I hope both audio and video are clear.
Yes, sir.
Yes, sir.
Okay, fine. So let's get started with the discussion in today's class. Last class, if you remember, we had done our discussions with respect to ideas of a circular current loop. We are done with gyromagnetic ratios and Bohr's magneton, isn't it?
Yes, sir.
We are done with gyromagnetic ratios and Bohr's magneton. Anything apart from it that we have discussed? No, is it? Bohr's magneton was the last concept discussed, or did I discuss anything else?
So we did talk to.
We did?
Torque.
Oh, we also did torque, isn't it? We got the expression for magnetic field is equal to BIA. N times torque is B cross N cross B, is it?
Yes, sir. Yes, sir.
Good. Cool. Well, so once these discussions are done, we are coming into the last part of this chapter where we'll be trying to understand one of the most important concept, that is the concept of moving coil galvanometer. Now, what is this moving coil galvanometer? Pretty simple. You all have been to labs, right?
Yes, sir.
There you have used a device called as galvanometer, which just deflects whenever current passes through it.
Yes.
Correct?
Yes, sir.
That itself is the moving coil galvanometer, and we'll be trying to understand how exactly that moving coil galvanometer works. Point number one. You will have to be very careful in trying to understand these ideas, right? Now, what is this, Andre? The amount of deflection, whatever the galvanometer produces, will be directly proportional to the strength of the current which is flowing through it. So if there is more current flowing, the deflection produced will be more. If there is lesser amount of current that is flowing, then the deflection produced will be less. There are two major experiments with respect to this concept. One is conversion of galvanometer into ammeter. The other one is conversion of galvanometer into voltmeter. I hope you have done at least one of these two in your labs.
Yes, sir.
Right? So this concept once again turns out to be very important because you have some aspects related to your lab exams also. And with respect to entrance, as usual, every nook and corner of your NCERT will be important. So let's begin our discussion with respect to trying and understanding how exactly this moving coil galvanometer works. Before I do that, I will just brush up what we have discussed in our previous session. In our previous session, we just discussed that if there is a current carrying loop placed in between the poles of magnet, it experiences a torque and it starts rotating. Correct? It starts rotating. I've told you, if this is the direction of the current, magnetic field is like this. Current direction is upward. So here force will be into the board. Here the current direction is downward, force will be out of the board. So one downward, one upward. Two equal and opposite forces will make this coil to rotate. Right? The torque value that this coil experiences is given by M cross B, where B is the strength of the magnetic field, M is the magnetic moment. Now, what is magnetic moment? Can you people tell me what is the formula for magnetic moment?
NIA.
Very good. It is the number of turns into strength of the current flowing through the conductor and area of the current loop under consideration. Into B, A cross B is AB sin theta, so M cross B is MB sin theta. So technically, this is the expression for strength of the torque that a particular coil would experience if it is placed in a uniform magnetic field. I hope there is no doubts or confusions with respect to this concept. Because in order to understand how a moving coil galvanometer works, this simple idea of a coil placed in a magnetic field, if current flows through it, it will start rotating. That simple idea you people should be clear with, right? So now first let's try to understand the construction of this. Construction of a moving coil galvanometer. Now the idea is pretty simple, people. What they have is, they have a cylindrical soft iron core, right? They have a soft cylindrical iron core. I'll just draw it here. Okay. So what you can see on the board here is a cylindrical soft iron core, correct? So I'll just change the color of this so that so this is what a cylindrical soft iron core. So soft iron core is that. What do I mean by this? It's just an iron piece which is cylindrical in shape. Now for the cylindrical soft iron core, what they do is they wind large number of turns of conducting wire, right? So this is one wire. There is one more wire like this. Similarly, lot of number of turns of the wire is wound around the cylinder. Hope you are able to visualize, right? Suppose let's say this is the cylinder. There is lot of wire which is wound to it like this. So that is what I'm trying to represent here, right? Now, on either side of this cylindrical loop or the cylinder, they place poles of powerful bar magnet, right? So suppose let's say this is one of the face. So let's say this is the south pole of the bar magnet. On the other side, they place the north pole of the bar magnet. Let's say. So what I am trying to write here is technically a three-dimensional diagram. Hope you are able to figure out. So this is the north pole. This is the south pole of a bar magnet. In between these two poles, there is a cylindrical soft iron piece which is kept. For this iron piece, they have wound wire, right? Then what they do is, for this cylindrical iron piece, they just simply attach a needle. They attach a needle, and that needle is made to read on a circular scale. Okay, this is the circular scale. See, what you will see in your lab is just this needle and the circular scale. The soft iron core wire and the magnets will be within the galvanometer setup that would be given to you, right? Along with this, there are also two springs attached to this. There is one spring attached at the top, that is S1. There is one more spring which is attached at the bottom, that is S2. So this is how the interior part of a moving coil galvanometer looks. Hope you are able to visualize what I am trying to write here. I'm not so good at drawing, but still I've tried to maintain a good drawing out here. So what I'm trying to tell you is, there are two powerful poles of bar magnet, north pole and south pole. The bar magnet are curved. They are carved to be semicircular in shape, right? Why do they do it? Is to make sure that the field is always normal to the current loop considered here. Now, between the poles of a bar magnet, there is a solid metallic cylinder placed. For this metallic cylinder, they wind wires, lot of number of terms of wires. Here I've just written 3 terms, but in general, there will be thousands and thousands of turns of wire which will be wound. That cylindrical iron core is connected to a needle. That needle is showing some reading on the circular scale. What you see is only the scale and the needle. Everything else will be enclosed within the pouch of the galvanometer, right? Now, how does this work? Is pretty simple. Now, if at all the ends of the wire, I've told you that there are wires connected, right? So this wire would have certain end here. This wire would have certain end here, right? These two ends of the wire would be connected to the notches in the galvanometer. You see one in red color, the other one in black color, isn't it? So you see a notch exactly at the bottom of the galvanometer. And you see one more of black color. Here black would not be visible, so I'm just writing it in two different colors. So one of the wire would be connected here, another part of the wire would be connected here. Now what happens when you connect a galvanometer is pretty simple. See, when you connect this galvanometer to an external circuit, let's say you connect it, what will happen? Current flows through the circular loops, right? Circular loop, it would be rectangular loop. So the current enters, it would flow through this large number of turns of the green wire. Now, this turns of the green wire is nothing but a current loop placed in a uniform magnetic field. Agreed? Just like there is a current loop in between the poles of the magnet, there are current loops in between poles of the magnet. So whenever current flows through this galvanometer, it will flow through the current loop placed in between the poles of the powerful bar magnet. Now, if there is a current loop placed in between the poles of a bar magnet, what should that current loop experience?
Torque.
Should experience a torque, due to which what should current loop do? Current loop should rotate, isn't it? Now, the green color current loops try to rotate, but since these green color current loops are attached to the cylinder, it will make the cylinder also rotate along with it. Now, since the needle is connected to the cylinder, the needle will also rotate and it will show some reading on the scale. Did you understand how a moving coil galvanometer works?
Yes, sir.
And it's pretty simple. You have a cylindrical loop. You have large number of turns of wire which is wound to it. There will be one north pole, one south pole cap. The moment current flows through the wire, it will be a current loop placed between poles of the powerful magnet, due to which it experiences a torque and rotate. Since the loop rotates, loop is attached to the cylinder, cylinder rotates, needle is attached to the cylinder. So needle will also rotate. That will show you some readings on the scale. Okay, then why are the springs S1 and S2 used in the diagram? See, in your examination, you don't have to write the notches and all. You just write this, more than sufficient. What is the purpose of the spring S1 and S2? It's pretty simple. See, once you connect galvanometer to the circuit, it will deflect. Once you switch off the current, what will happen to the needle?
Comes back to zero.
It will go back to its original position. Oh, you will not pull it back. It will go back automatically by itself. Agreed?
Yes, sir.
How will that go back automatically by itself? It's only because of these two springs, S1 and S2. Imagine there is a cylinder, there is a needle. This cylinder is connected to a spring. When needle rotates, it will twist the spring also. Correct? When needle rotates, the cylinder rotates. Cylinder is connected to the spring, so it will twist the spring. Correct? Imagine there is a spring. This rotates and the spring gets twisted. Correct? So until and unless current flows, there is a torque due to electric current, because of which needle will continue to push forward. The moment current stops, the spring which would have twisted will have no force acting on it. So what will happen to the spring? It will untwist itself. It comes back to original position. Agreed. Imagine what happens if you twist a spring and leave. It will come back, isn't it? Same thing. When current is there, the springs gets twisted. The moment current gets off, the spring uncoils themselves. Since the spring uncoils, due to which it is connected to the cylinder also rotates back, the needle will also come back to its original position. So that is how a moving coil galvanometer works. Is this idea clear to everybody? Any
So
doubts?
could you explain once more?
Which part exactly?
So the current moving part, like the twisting part.
Twisting part, is it?
Yes, sir.
Okay. See, when current flows through this coil, the coil rotates, due to which the needle rotates, correct?
Yes, sir.
Now the cylinder is connected to the spring. So when this rotates, what happens to the spring? The spring gets twisted, isn't it?
Yes, sir.
Now the moment current stops, what should the spring do? It should recoil back.
Yes.
When it recoils, since it is connected to the cylinder also turns back.
Yes, sir.
The needle should also come back. So when current is there, needle goes forward. When you switch off the current, it will go back to its original.
Yes, sir. Got it.
So that is how a moving coil galvanometer works. Now, once you have understood these ideas of moving coil galvanometer, let me try to go ahead and tell you people about a bit of mathematics related to moving coil galvanometer. Very, very important aspects. Just carefully observe. We know that the torque that this loop experiences will be M cross V, isn't it? Or I say torque will be equal to mb sin theta. Now we need to understand that every time, since the magnets are curved, the field will be radial. So if you have a loop here, the loop will always have its area vector perpendicular to the magnetic field. That is why they have made it radial. So always consider that the arrangement is made such that theta is 90 degree. So what will happen to the torque? The torque will turn out to be mb. Magnetic moment, we know number of turns into current into area of the loop into strength of the magnetic field. This is the torque produced because of the electric current, correct? Now imagine people, suppose let's say when I connect this galvanometer needle twists and it stands at one position, right? If the current is pretty weak, it just goes slightly forward and it stops there. Now let's try to understand exactly at the position where it stops. Now when the needle is at rest, is there any torque acting on it?
No.
If at all there was total torque, it would have continued to rotate, correct? I'm telling you that it has stopped. That means the total torque should not be there. Then where did the torque, this produced torque go on there? It is cancelled by the opposite torque produced by the twisted springs. Are you getting my idea? Look here. This is the circular cylinder. It turns. It will twist the spring. So just like as much as you twist the spring, what happens to the force with which it unwinds? You take a spring, you twist.
Will be greater.
It comes back. You take the same spring, twist it more and leave. It comes back with a greater torque.
Yes.
So, as and when this coil is rotating, the opposite torque in the spring also increases. Right? I call it as the restoring torque because that is the torque which tries to bring the spring back to its original position. So, it so happens the torque is rotating the coil. The restoring torque is increasing. At one point, it becomes equal to the torque produced by the electric field. So then what will happen to the total torque? Both the torques are equal, both the torques are opposite. So what will happen to the total torque?
0.
Total torque will turn out to be 0. Did you understand this concept?
Yes.
I'll repeat it again. Listen. This circular loop, or let's say this cylindrical iron core, when it rotates, it will twist the spring. So what will the spring do? The spring will try to bring this coil back. So it has a torque whose direction is opposite to the rotation of the spring or the needle, correct? Now, if the needle rotates more, the restoring torque keeps on increasing. If it increases and sometime at some point, if it becomes equal to the torque produced by the electric field, then electric field will try to push it with 20 Newton meters of torque to right. Spring will try to push it back with the same 20 newtons of torque so that the net torque will be zero. Needle stops there. Got it?
Yeah.
Yes.
Yes.
Okay. Now I will have to try and understand the expression for the torque produced in the spring. Now this understanding is pretty simple. See, the restoring torque that is produced in the spring, what does it depends on? It depends on the amount of angle by which the spring is twisted. If you twist more, restoring torque will be more. Agreed?
Yes.
So I say that restoring torque is directly proportional to phi. Or I say torque is some constant K times phi. This constant of proportionality is called as couple per unit twist. So what is this constant of proportionality called? This constant of proportionality is called as couple per unit twist. Now at equilibrium, what will happen, people? The torque in the spring and torque produced by the current loop, both will be
Equal.
equal. So can I equate the left hand sides of both? I'll write at equilibrium. At equilibrium, what can I say? The torque produced in the spring should be equal to torque produced by the current loop. So I can say I is equal to K divided by NAV into phi. Agree?
Yes, sir.
Now, see, K is couple per unit twist, which is a constant for a given spring. If I give you a spring, the constant doesn't change. Number of turns is constant, area of the loop is constant, strength of the magnetic field is constant. So can I say all these are constants?
Yes.
Now, now can I say, since I can write if one is proportional to something, I can write that is equal to constant into something. If it is equal to constant into something, then I can write it in reverse order saying that current is directly proportional to phi. This is what is the principle of working of a galvanometer. If you produce more current, then there will be more deflection. What is phi? Phi is the angle by which the needle rotated, correct? So if you pass more current, there is more deflection. If you pass lesser current, there will be lesser deflection. That is what is the principle of working of a moving coil galvanometer. Is this idea clear to everybody?
Yes, sir.
Okay.
Yes, sir.
Can you have a quick note of this discussion? Monday is a government holiday for you. When are you all compulsorily coming to college? You come during midterms, right?
Yes, sir.
Okay. Tuesday is your college working? It's functioning, right?
Yes, sir.
Yes, sir.
Okay. If at all Monday is a holiday, then we'll give materials on Tuesday. If Tuesday is not a holiday, sorry, if Monday is not a holiday, we'll give it on Mondays.
Monday is mostly on this.
Yeah, probably it will be a holiday. If it's holiday, then we'll have additional classes on that day in morning only. We will give notes on Tuesday. And one request, people, there are a lot of students who have absolutely not paid their fees only, the second installment, the third installments and all. So please make sure that you make the payments before Monday or Tuesday, right? You still have 2 to 3 days of time. If at all there are any concerns, please let me know. But make sure you clear whatever the balance amount is, right? Those who have already paid need not worry. Those who have not paid, please make it at the earliest. I think no institute will live like this also. No? Every time they keep on calling you to remind you to pay the fees. At PACE, we don't do that also. We expect you people to pay it by yourself. So make sure you make the payment before Monday. Sir, when the restoring torque is cancelled out, the needle won't return to its original position when current stops. Okay. Vaisnavya, who is that? Priyadarshini, look here. See, when it is at rest, there is backward pulling force also, there will be forward pulling force also. So it will neither move back nor move front. When current stops, the forward pulling force becomes zero, but the backward pulling force will still be there, no, which will make the needle to come back. Got it? Cancel and it will not vanish. It will be there, but its effect is cancelled by the other. Vaisnavi, how is it 90 degree? Andre, the magnets are carved in the circular form, correct? Now this plane is perpendicular to the magnetic field produced. Look here, the magnetic field will be produced like this. This is the plane like this, right? Or wait, it should be perpendicular to area vector, isn't it? This is a 3D diagram. Let's say this is the area vector. The magnetic field will be from this end to that end. It will be radial magnetic field, north to south. So this is the field, this is the area vector, this angle will be 90. Got it? Vaishnavi?
Yes, sir.
Yeah. College alla agidya? Moving coil galvanometer.
Yes, sir.
So it would be more of like revision, right? So this is what is exactly there in your laboratories. See, they say resistance of the galvanometer, right? Figure of Meritel.
Yes.
Resistance of the galvanometer, andre, they are basically talking about the resistance of this wire which is wound inside. Aita, shall we move ahead?
Yes, sir.
Yeah.
Okay. Now, listen. Let me go back to the same discussion. There are a few technical terms that you will have to understand with respect to a galvanometer. What is that, Andre? The first one is trying to understand what do we exactly mean by current sensitivity. See, the idea of current sensitivity, remember this current sensitivity is defined for a galvanometer. For example, you can find out what the value of current sensitivity in your lab also. What is this current and sensitivity? It is basically how much angle of deflection is produced per unit current. Okay? If you pass 1 ampere of current, how many degrees will the needle rotate? That much sensitive the galvanometer will be. If current sensitivity is very high, then for 1 ampere of current, there will be large angular deflection. So even small current galvanometer will deflect more. I can say that galvanometer is more sensitive. Did you understand what do I mean by current sensitivity? It basically gives you an information about the amount of deflection produced in a galvanometer when a unit current flows through it. Artha? So now, from this expression, if you take I to left hand side, NAB by K will be on right hand side. Correct? So this is what is the formula for current sensitivity. SI unit will be radians per ampere. Theta is measured in radians, current is in ampere, so it is radians per ampere. So if you want the galvanometer to be more sensitive, should you have more number of turns in it or less number of turns? What do you think? Are you people there in the meeting? ಕೇಳಿಸ್ತಿದ್ಯಾ ನಾನು ಮಾತಾಡ್ತಿರೋದು?
Yes,
Yeah.
sir.
Did you understand what current sensitivity is?
So could you repeat?
Yeah. Listen. See, current sensitivity basically tells you an information about how much deflection will this galvanometer produce when you pass 1 ampere of current. Look here, you have a galvanometer, right? I'll give you a galvanometer. You connect it to a battery and you make 1 ampere of current flows through it. You see that the galvanometer deflects by 30 degrees. Then can I say this galvanometer deflects 30 degrees for 1 ampere of current?
Yes, sir.
Yes, sir.
This itself is called as current sensitivity. Then how much will that galvanometer deflect for 2 amperes of current?
60 degrees.
60 degrees.
60. So current sensitivity is basically this value, the amount of deflection produced per unit current. For example, if a galvanometer deflects by 180 degrees when 18 amperes of current flows through it, what should be its current sensitivity? See, 180 degrees is for 18 ampere. Current sensitivity is how many degrees for 1 ampere? Correct?
10.
So
10.
current sensitivity value will be 180 divided by 18. That will be 10 degrees per ampere. Gotaita?
Yes, sir.
So it is basically in general the deflection produced divided by the current value. Correct? Deflection by current. Deflection by current. That is what is current sensitivity. Did you understand this?
Yes, sir.
So if
Yes,
a galvanometer is given to you, you try and do this next time in your lab. You take a galvanometer, try to pass small amount of current through it, maybe 0.1 ampere or 0.2 ampere, or you try to pass. Find out how much degrees it rotates. Alle scale mele nodi. You divide the deflection by the current, you get the current sensitivity of that galvanometer. Right? Or ask your teachers to do. They will not, then you only try. Now this current sensitivity is there, right? Next we will try and understand what voltage sensitivity is there. Can you guess what should this voltage sensitivity be? If current sensitivity is deflection produced per unit current, then voltage sensitivity should be deflection produced per unit voltage.
Yes, sir.
Correct? You imagine there is a galvanometer. Okay. You go and connect it to a battery of 1 volt. It will produce some deflection. The amount of deflection is its voltage sensitivity. Deflection produced for 1 volt. Correct? So that is what is voltage sensitivity. Can I write this voltage as current into resistance? V is equal to IR.
Yes, sir.
See, this is voltage sensitivity. And what is this? This is current sensitivity. IS and the current sensitivity, VS and the voltage sensitivity. Now, what is this phi by I, people?
Current sensitivity.
So can I write this as IS divided by R?
Yes, sir.
Now tell me what resistance is this R? Where will this current flow? This current will flow through the galvanometer. So this R should be the resistance of the galvanometer. Got it? Where R is the resistance of the galvanometer. Can you tell me what should be the SI unit of this? Radians per volt, is it?
Yes, sir.
Did you understand both the terms, current sensitivity and voltage sensitivity? Have a quick note of them. Tell me once you're done. Am I fast? Is the speed okay?
Yes, sir.
Yes, Trisha. We'll move to the next.
Yes.
Okay. Once these two discussions are done, I will try to give you information about one more very similar kind of understanding. That is the concept of figure of merit of a galvanometer. Now let's try to understand what figure of merit. Figure of merit is pretty simple. How much current is required for the galvanometer to show 1 degree of deflection? Remember, don't get confused. Current sensitivity is how much deflection will the galvanometer produce when current is 1 ampere. Figure of merit is how much current is required for the galvanometer to produce 1 degree of deflection. So figure of merit is basically I divided by 5. Current sensitivity is 5 by I. So figure of merit is I by 5. Did you understand this? See, if galvanometer shows 1 degree of deflection, let's say for 1.5 amperes of current, then figure of merit is said to be 1.5 ampere per degree. Got it? Andre, for 1 degree of deflection, how much current is required? For example, I'll give you a galvanometer, right? You find out and tell me how much current is required for 1 degree of deflection. So what you do? You pass current through it, you measure the degrees, divide the current value by the deflection, so you get the current required for 1 degree of deflection. So current required for 1 degree of deflection is figure of merit. Deflection produced for 1 ampere of current is current sensitivity. Did you understand the difference between these two?
Yes.
Yes, sir.
What is the formula for this? It should be reciprocal of current sensitivity. And remember, don't get confused with this. There are two terms called as K here. Figure of merit is generally indicated by capital K. What is this K?
Small k.
What does that represent? What was that K? Where did it come from?
Couple per unit.
It is couple per unit twist. Artha, don't get confused between small k and capital K. We know this is small, this is capital, but what do they represent? Capital K represents figure of merit. Small k represents what?
Couple per unit.
Couple per unit twist. Got it? So this is what is the concept of figure of merit. Have a quick note of this also. November 20th is your midterm, is it?
Yes, sir.
Yes.
So Sundays, I think few of you had messaged me that all of you are comfortable after 9. Correct?
Yes, sir.
So we'll have class starting from 9:30 to 11. If Gupta sir has a CET class, it will be from 11:30. So there will be no class. I have a class from 8 to 9:30. Immediately after that, I'll start your class. Okay?
Yes, sir.
So from Tuesday, I will plan for offline classes. At least now you people should be ready. Last time when I asked, a lot of you message that I can't come. At least now you people should be ready. It has been so many days since things started to fall back normal. Priyadarshini, we will start now. Probably this week only we will start. Physics only one chapter CET is done, right? The rest should happen. I think I have also done synopsis of second chapter. No? Okay. Only problems of second chapter it's pending. Done with this?
Yes, sir.
Okay. Now we will move on to one of the most important application of this. That is conversion of galvanometer into a voltmeter. Right? So now, how do I do this? You know a galvanometer, you know an ammeter, you know a voltmeter. An voltmeter will show you the voltage readings. A galvanometer will show whether the current is there or not. An ammeter will give you the measurement of current, isn't it? So now, how do I convert a galvanometer into an voltmeter or an ammeter? So if you want to convert one device to another, you need to understand the difference between all three devices. The idea is pretty simple here, people. See, what exactly happens is, let it be a galvanometer, or let it be an voltmeter, or let it be an ammeter. How they work is all the same. If you look into the devices, they all look same also, correct? Almost. But what is the difference, Andre? The major difference lies in the value of resistance of this device. Sir, how, Andre? Look here. What should be the resistance of an ideal voltmeter? I have done that discussion when I explained you zero current devices and potentiometer. What should be the resistance of an ideal voltmeter? Should voltmeter draw current through it? Say yes or no. Okay, do one thing. One say yes, another say no. One of that will be correct. What should be the resistance of an ideal voltmeter? Haven't I told you? If there is a resistor, if I connect an voltmeter in parallel, all the current should flow through resistor only. No current should flow through voltmeter if it is ideal, correct? So what should be the resistance of an ideal voltmeter? Should it be very high or should it be very low?
High, sir.
It should be very high. So can I say resistance of an ideal voltmeter should be infinity? What should be resistance of an ideal ammeter?
Low.
Ammeter should allow all the current to flow through it. Only then it can measure, correct?
Yes, sir.
If it is allowing all the current to flow through it, its resistance should be 0. We know that galvanometer resistance will be some moderate value R. It will neither be infinity, it will not be 0. It will be some intermediate. This is the ideal situation. Practically what happens, the voltmeter resistance will be around few thousand ohms. Ammeter resistance will be around 1 or 2 ohms. Galvanometer resistance would be around 80 ohms. Just for your understanding, you can compare with numbers in the kodtare. Okay. So voltmeter, galvanometer and an ammeter all works on the same principle. All three devices has a coil, has magnet, has wire, has needle, has circular scale. In all this, the moment current flows, deflection takes place. But the difference in all these three devices is an voltmeter will have a very high value of resistance. Practically, ideally, it should be infinite. An ammeter should have ideally zero resistance. Practically, it will be few ohms, 1 or 2 or 3 ohms. A galvanometer has some sufficient amount of voltage, maybe around 80 ohms or 100 ohms or 120 ohms. Not in thousands at all, within hundreds it will be. Now, if I want to behave or if I want to make a galvanometer to behave like an voltmeter, what should I do?
Increase or decrease the resistance.
I should increase the resistance of the galvanometer, right? Because the way all the three devices work is the same. The only difference is in the resistance. So if I somehow increase the resistance of a galvanometer to a very high value, the galvanometer automatically starts behaving like an voltmeter. Now, if I want to increase the resistance, what type of connection should I make? Series or parallel? I want to increase the resistance. What will happen?
Series.
A series combination, because if you connect a resistor in parallel, effective resistance will be less than the least. So you are basically reducing. If this is 80, suppose let's say you connect 5000 in parallel, effective resistance will be less than 80. You did not increase, you decrease if you connect parallel. So if I want to make a galvanometer behave like a voltmeter, I should overcome the difference between these two devices. We know that a voltmeter has a very high resistance. So by some means, if I increase the resistance of the galvanometer to a very high value, then that galvanometer will start behaving like an voltmeter. Is this concept clear to you all?
Yes.
Okay. Now, let me understand the mathematics behind it. Suppose, let's say, I have a device. Let's say this is the galvanometer. Let G be the resistance of the galvanometer. Now, suppose let's say there is a current flowing through the galvanometer. Let's say I. Okay. Now, when you make the conversion, you should know how much voltage should galvanometer read. For example, let's say the galvanometer that you had has 30 divisions, right? So upon the needle deflecting to the last point, you can read up to 30 volt, right? Suppose if you decide that 1 degree deflection for 1 volt, then 30 degrees of deflection will be showing at 30 volts of voltage, correct? Are you able to understand?
Yes, sir.
The full scale deflection should read the maximum voltage. That is what I am trying to tell you. Suppose if you want a galvanometer to measure a maximum of 30 volts, what are you supposed to do? The full scale deflection of the galvanometer should be equal to 30 volt. So if there are 30 divisions and 30 volt is what you are supposed to measure, then each division will measure 1 volt. Arthat is a simple mathematics I am trying to tell you. So if suppose if 20 volt is the maximum voltage you would like to measure, then what should be the value of full scale deflection of the galvanometer? It should read 20 volt, right?
Yes, sir.
Yes, sir.
If 40 volt is the maximum voltage that you want to measure using this galvanometer, then when you connect this galvanometer to 40 volt, this galvanometer should show full scale deflection, right? Full last needle it should show, correct?
Yes, sir.
Yes, sir.
So what I will be looking into is, suppose if I want to make this galvanometer read a maximum voltage value of V, then when voltage is V, shouldn't this galvanometer show full scale deflection?
Yes, sir.
Now listen, if K is the value of current sensitivity and theta is the number of deflections, can I say K into theta is the current required for full scale deflection? I repeat, listen. What do I mean by K? K is figure of merit. What do I mean by figure of merit? Amount of current required for 1 degree deflection. Suppose if the galvanometer has 30 degrees of deflection, then current required for 30 degrees of deflection will be K into theta.
Yes, sir.
Are you getting my point? Look here, K and current required for 1 degree of deflection, correct? So suppose let's say I give you a galvanometer which has 30 degrees and current for each degree deflection is 2 amperes. So how much current should flow through this galvanometer for it to show complete full scale deflection? K value is 2 ampere, theta value is 30. So how much should be the current that should flow through the galvanometer to show full deflection?
2 into
60.
60, correct?
60.
60 amperes should be the current. So in general, if K is figure of merit, theta is the maximum number of deflections in the galvanometer, then current required for full scale deflection is K into theta. Agreed with this, everybody?
Yes.
Okay, now listen. Now if I want to convert this galvanometer into an voltmeter, let's say of range V volt, okay, then I should increase the resistance of the galvanometer. So if I increase the resistance of the galvanometer, how can I do it? I can connect a large resistance in series with the galvanometer. Agreed?
Yes, sir.
Now listen. So now this galvanometer along with the newly added resistor put together will now behave like what? It will now behave like voltmeter. Got it?
Yes, sir.
Now listen. Suppose if this galvanometer has to measure a voltage V, so then voltage across the galvanometer will be V. What will be the voltage across the resistor? Voltage across the resistor will be Ig into R, correct? Because when I try to measure a voltage V, the maximum current that should flow through this galvanometer is this, right? So I say the total voltages, voltage across the galvanometer plus voltage across the resistor, right? Now, the total voltages, voltage across the galvanometer will be current required for the galvanometer to show full scale deflection into resistance of the galvanometer plus this is Ig into R. So can I say this to be Ig into G plus R? Now listen, V divided by Ig is equal to G plus R. So what should be the resistance value that I should be connecting in series? It should be V by Ig minus G. This is slightly a bit of concept which is slightly slightly complex. I'll re-explain this once again. Just carefully understand. Listen to each and every word carefully. what I want is, I want to make this galvanometer measure a voltage value V. What does that mean? When I connect that galvanometer to a voltage source V, how much deflection should it show?
Maximum.
It should show full scale deflection, correct? If there are theta degrees in it, it should show full deflection when I try to connect it to a voltage V, because V is the maximum voltage I would like to measure. So, what I do is, if V is the maximum voltage that I would like to measure, then when I connect my device to that voltage source, my device should show full scale deflection. So for device to show full scale deflection, how much current should flow? K into theta is the value of current that should flow. So what do I mean by Ig here? Ig is the current for the galvanometer to show full scale deflection. Now the difference between a galvanometer to voltmeter is that the resistance. So if you increase the resistance of the galvanometer will start behaving like an voltmeter. So how do you increase the resistance? You increase the resistance by connecting some high value of resistance in series with the galvanometer. The combination of the galvanometer and newly connected resistance of R will totally togetherly behave like a voltmeter, because working is same. Resistance was the only difference. I have overcome the difference in resistance by adding a high value of resistance. So if I want to convert the galvanometer, what is the value of R that I am supposed to connect in, right? Do the mathematical calculations. In series combination, what divides? Will voltage divide or will current divide?
Voltage.
Voltage divide. So there should be some voltage across the galvanometer, some voltage across the resistor. The total voltage should be V voltage across galvo plus voltage across resistor, correct?
Yes, sir.
Yes, sir.
Now when I am trying to measure this voltage V, this galvanometer should show full scale deflection only, because V is the maximum voltage I would like to measure. So galvanometer should show maximum deflection. So current flowing through the galvanometer should be Ig only, correct? If it is greater than Ig, then deflection will be beyond. If it is less than Ig, deflection will be small. We don't want both of these things to happen. This galvanometer should exactly show the complete last reading. For that, the current that should flow must be Ig. Since G and R in series, current flowing through G and R will be same. So voltage across galvanometer will be current into resistance of the galvanometer, that is Ig into G. Voltage across resistor will be current into resistance of the resistor, that is Ig into R. Take Ig common, shift Ig to left hand side. What you wanted is the value of resistance that you are supposed to connect. So keep it on one side, send G to other side. If you send G to other side, it will be V by Ig minus G is equal to R. So suppose, let's say, I'll give you a galvanometer where the current required for full scale deflection was 2 ampere. Resistance of the galvanometer was 80 ohms. And I want to make this galvanometer to measure a maximum of 3 volt. Number of deflections was 30. So how much resistance are you supposed to connect in series with it? You can calculate using this value, this formula. Now in this formula, what is V? V is the maximum voltage that you would like to measure and the range. So I have given it to be 3 volt. Current through galvanometer is 2 ampere. Minus resistance of the galvanometer is 80. So you substitute this, you find the value, you get the value of resistance, connect that in series with the galvanometer, you get that. Got it?
Yes, sir.
If you understand how to convert a galvanometer into a voltmeter, just look through the entire concept. People, tell me if you have doubts at any of the aspect of it. Conversion to ammeter, we will do it in next class so that you don't get confused between both. Did you all understand?
Yes,
Yes,
sir.
sir.
A galvanometer and an voltmeter are same. So then what is the difference between them? And it's only in the resistance. galvanometer has lesser resistance when you compare it to the voltmeter resistance. So if you somehow increase the resistance of the galvanometer, it will behave like an voltmeter. So if you want to convert a galvanometer into an voltmeter, connect a high resistance in series to it. But be more technical. If you want to measure a voltage value V, then when that voltage is connected for this device, the galvanometer should show full scale deflection. So current should be Ig, voltage should be sum of the voltage across G and R. You should know what is Ig. Ig is current for galvanometer to show full deflection. That is figure of merit into angle T. So ಇಲ್ಲಿ total voltages, resistance R, do the mathematics, you can get the formula for resistance that is to be connected in series. Can you have a quick note of this? Doubt idre keli, don't hesitate. If you don't understand, if you just simply by heart, see, this is a very important question for 3 marks in your board exam also. You can by heart and however write, you can remember all the figures like cartoon and write, but you will fall in MCQs. Can you take the screenshot of it so that we will, I'll be a bit early to my next class. So it's already 5:15. I have 10 minutes to go there. Take the screenshot of this, people.
Okay, sir.
We will continue. Only one simple topic is left in this chapter, that is conversion of galvanometer to ammeter. So we'll leave. I'll end the meeting.
Yes,
Yes.
sir.
Thank you.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.